Machine learning, a branch of artificial intelligence, concerns the construction and study of systems that can learn from data. For example, a machine learning system could be trained on email messages to learn to distinguish between spam and non-spam messages. After learning, it can then be used to classify new email messages into spam and non-spam folders. The core of machine learning deals with representation and generalization. Representation of data instances and functions evaluated on these instances are part of all machine learning systems. Generalization is the property that the system will perform well on unseen data instances. The conditions under which this can be guaranteed are a key object of study in the subfield of computational learning theory. There are a wide variety of machine learning tasks and successful applications. Optical character recognition, in which printed characters are recognized automatically based on previous examples, is a classic example of machine learning. Definition: in 1959, Arthur Samuel defined machine learning as a field of study that gives computers the ability to learn without being explicitly programmed. Tom M. Mitchell provided a widely quoted, more formal definition: a computer program is said to learn from experience E with respect to some class of tasks T in performance measure P, if its performance of tasks in T, as measured by P, improves with experience E. This definition is notable for its defining machine learning in fundamentally operational rather than cognitive terms, thus following Alan Turing's proposal in Turing's paper Computing Machinery and Intelligence that the question "Can machines think?" be replaced with the question "Can machines do what we can do?" Generalization: a core objective of a learner is to generalize from its experience. Generalization in this context is the ability of a learning machine to perform accurately on new, unseen examples tasks after having experienced a learning data set. The training examples come from some generally unknown probability distribution, and the learner has to build a general model about this space that enables it to produce sufficiently accurate predictions in new cases. Machine learning and data mining, these two terms are commonly confused, as they often employ the same methods and overlap significantly. They can be roughly defined as follows: machine learning focuses on prediction, based on known properties learned from the training data. Data mining focuses on the discovery of unknown properties in the data. This is the analysis step of knowledge discovery in databases. The two areas overlap in many ways. Data mining uses many machine learning methods, but often with a slightly different goal in mind. On the other hand, machine learning also employs data mining methods as unsupervised learning, or as a pre-processing step to improve learner accuracy. Much of the confusion between these two research communities comes from the basic assumptions they work with. In machine learning, performance is usually evaluated with respect to the ability to reproduce known knowledge, while in knowledge discovery and data mining the key task is the discovery of previously unknown knowledge. Evaluated with respect to known knowledge, an uninformed method will easily be outperformed by supervised methods, while in a typical KDD task, supervised methods cannot be used due to the unavailability of training data. Human interaction: some machine learning systems attempt to eliminate the need for human intuition in data analysis, while others adopt a collaborative approach between human and machine. Human intuition cannot, however, be entirely eliminated, since the system's designer must specify how the data is to be represented and what mechanisms will be used to search for a characterization of the data. Algorithm types: machine learning algorithms can be organized into a taxonomy based on the desired outcome of the algorithm or the type of input available during training the machine. Supervised learning algorithms are trained on labeled examples, that is, input where the desired output is known. The supervised learning algorithm attempts to generalize a functional mapping from inputs to outputs, which can then be used speculatively to generate an output for previously unseen inputs. Unsupervised learning algorithms operate on unlabeled examples, that is, input where the desired output is unknown. Here the objective is to discover structure in the data, not to generalize a mapping from inputs to outputs. Semi-supervised learning combines both labeled and unlabeled examples to generate an appropriate function or classifier. Transduction, or transductive inference, tries to predict new outputs on specific and fixed cases from observed, specific cases. Reinforcement learning is concerned with how intelligent agents are ought to act in an environment to maximize some notion of reward. The agent executes actions which cause the observable state of the environment to change. Through a sequence of actions, the agent attempts to gather knowledge about how the environment responds to its actions, and attempts to synthesize a sequence of actions that maximizes a cumulative reward. Learning to learn learns its own inductive bias based on previous experience. Developmental learning, elaborated for robot learning, generates its own sequences of learning situations to cumulatively acquire repertoires of novel skills through autonomous self-exploration and social interaction with human teachers, and using guidance mechanisms such as active learning, maturation, motor synergies, and imitation. Machine learning algorithms can also be grouped into generative models and discriminative models. Theory. The computational analysis of machine learning algorithms and their performance is a branch of theoretical computer science known as computational learning theory. Because training sets are finite and the future is uncertain, learning theory usually does not yield guarantees of the performance of algorithms. Instead, probabilistic bounds on the performance are quite common. In addition to performance bounds, computational learning theorists study the time complexity and feasibility of learning. In computational learning theory, a computation is considered feasible if it can be done in polynomial time. There are two kinds of time complexity results. Positive results show that a certain class of functions can be learned in polynomial time. Negative results show that certain classes cannot be learned in polynomial time. There are many similarities between machine learning theory and statistical inference, although they use different terms. Approaches. Decision tree learning. Decision tree learning uses a decision tree as a predictive model which maps observations about an item to conclusions about the item's target value. Association rule learning. Association rule learning is a method for discovering interesting relations between variables in large databases. Artificial neural networks. An artificial neural network learning algorithm, usually called neural network, is a learning algorithm that is inspired by the structure and functional aspects of biological neural networks. Computations are structured in terms of an interconnected group of artificial neurons, processing information using a connectionist approach to computation. Modern neural networks are nonlinear statistical data modeling tools. They are usually used to model complex relationships between inputs and outputs, to find patterns in data, or to capture the statistical structure in an unknown joint probability distribution between observed variables. Inductive logic programming. Inductive logic programming is an approach to rule learning using logic programming as a uniform representation for input examples, background knowledge, and hypotheses. Given an encoding of the known background knowledge and a set of examples represented as a logical database of facts, an ILP system will derive a hypothesized logic program which entails all the positive and none of the negative examples. Inductive programming is a related field that considers any kind of programming languages for representing hypotheses, such as functional programs. Support vector machines. Support vector machines are a set of related supervised learning methods used for classification and regression. Given a set of training examples, each marked as belonging to one of two categories, an SVM training algorithm builds a model that predicts whether a new example falls into one category or the other. Clustering. Cluster analysis is the assignment of a set of observations into subsets so that observations within the same cluster are similar according to some pre-designated criterion or criteria, while observations drawn from different clusters are dissimilar. Different clustering techniques make different assumptions on the structure of the data, often defined by some similarity metric and evaluated for example by internal compactness and separation between different clusters. Other methods are based on estimated density and graph connectivity. Clustering is a method of unsupervised learning, and a common technique for statistical data analysis. Bayesian networks. A Bayesian network, Belief network or directed acyclic graphical model is a probabilistic graphical model that represents a set of random variables and their conditional independencies via a directed acyclic graph. For example, a Bayesian network could represent the probabilistic relationships between diseases and symptoms. Given symptoms, the network can be used to compute the probabilities of the presence of various diseases. Efficient algorithms exist that perform inference and learning. Reinforcement learning. Reinforcement learning is concerned with how an agent ought to take actions in an environment so as to maximize some notion of long-term reward. Reinforcement learning algorithms attempt to find a policy that maps states of the world to the actions the agent ought to take in those states. Reinforcement learning differs from the supervised learning problem in that correct input-output pairs are never presented, nor suboptimal actions explicitly corrected. Representation learning. Several learning algorithms, mostly unsupervised learning algorithms, aim at discovering better representations of the inputs provided during training. Classical examples include principal components analysis and cluster analysis. Representation learning algorithms often attempt to preserve the information in their input but transform it in a way that makes it useful, often as a pre-processing step before performing classification or predictions, allowing to reconstruct the inputs coming from the unknown data-generating distribution, while not being necessarily faithful for configurations that are implausible under that distribution. Manifold learning algorithms attempt to do so under the constraint that the learned representation is low-dimensional. Sparse coding algorithms attempt to do so under the constraint that the learned representation is sparse. Multilinear subspace learning algorithms aim to learn low-dimensional representations directly from tensor representations for multidimensional data, without reshaping them into vectors. Deep learning algorithms discover multiple levels of representation, or a hierarchy of features, with higher-level, more abstract features defined in terms of lower-level features. It has been argued that an intelligent machine is one that learns a representation that disentangles the underlying factors of variation that explain the observed data. Similarity and metric learning. In this problem, the learning machine is given pairs of examples that are considered similar and pairs of less similar objects. It then needs to learn a similarity function that can predict if new objects are similar. It is sometimes used in recommendation systems. Sparse dictionary learning. In this method, a datum is represented as a linear combination of basis functions, and the coefficients are assumed to be sparse. Let X be a d-dimensional datum, D be a D by n matrix, where each column of D represents a basis function. R is the coefficient to represent X using D mathematically. Sparse dictionary learning means the following where R is sparse. Generally speaking, n is assumed to be larger than D to allow the freedom for a sparse representation. Methods for sparse dictionary learning include KSVD. Sparse dictionary learning has been applied in several contexts. In classification, the problem is to determine which classes a previously unseen datum belongs to. Suppose a dictionary for each class has already been built. Then a new datum is associated with the class such that it's best sparsely represented by the corresponding dictionary. Sparse dictionary learning has also been applied in image denoising. The key idea is that a clean image path can be sparsely represented by an image dictionary, but the noise cannot. Applications for machine learning include: in 2006, the online movie company Netflix held the first Netflix Prize competition to find a program to better predict user preferences and improve the accuracy on its existing Cinematch movie recommendation algorithm by at least 10%. A joint team made up of researchers from AT&T Labs Research in collaboration with the teams Big Chaos and Pragmatic Theory built an ensemble model to win the grand prize in 2009 for $1 million. In 2010 the Wall Street Journal wrote about a money management firm Rebellion Research's use of machine learning to predict economic movements. The article talks about Rebellion Research's prediction of the financial crisis and economic recovery. Software suites containing a variety of machine learning algorithms include the following: open source software, commercial software, journals and conferences, machine learning, Journal of Machine Learning Research, Neural Computation, International Conference on Machine Learning, Conference on Neural Information Processing Systems, see also. Systems Biology and Machine Learning, References. Further reading. External links, International Machine Learning Society, popular online course by Andrew Ng, at ml-class.org. It uses GNU Octave. The course is a free version of Stanford University's actual course taught by Ng, whose lectures are also available for free. Machine Learning Video Lectures.